All right, welcome to the Explainer. Today, we are diving into something that, can feel like a bit of a chore at first, the derivatives of trigonometric functions. I know, it sounds like a bunch of formulas you just have to memorize, right? But what if I told you there's this really cool, kind of beautiful pattern hiding inside all of it? We're going to find that pattern today, and you'll see how everything clicks together perfectly.
So, to get started, let's just think about a question. Picture a perfect wave in your mind. Like the kind you see on an oscilloscope, or maybe ripples spreading out on a lake. Now imagine you could figure out the steepness, the slope, at every single point along that wave. What would a graph of that slope even look like? Any guesses?
Well, in the world of math, that perfect wave has a name. It's the sine function. Y equals sine of x. You know the one. It just goes up and down, in this super smooth, predictable way. And if you look closely, right at the very top of each peak and the bottom of each valley, the curve flattens out for just a split second, right? That means the slope there is 0. But everywhere else, the steepness is always changing. Okay, so here is the really cool part. What happens if you actually plot out the value of that slope for every single point on the sine wave? You actually get another wave. And get this, it isn't just some random wave. It's a perfect, exact match for the cosine function. How wild is that? So our eyes are telling us something here. This visual guess is our starting point, so let's see if we can actually prove it.
Okay, let's dive into the core pair, sine and cosine. We're going to confirm that visual guess we just made.
And yep, calculus totally backs up what we saw. The derivative of sine of x, which is just the fancy way of saying the formula for its slope, is exactly cosine of x. Boom! That's our first big rule, locked and loaded. So what about cosine? Well, its derivative is almost the same idea, but with a little twist. The derivative of cosine of x is negative sine of x. That little minus sign is super important. And with just these two rules, we now have the building blocks for literally everything else. All right, now we're going to build the rest using rules we already know. And here's where it gets really efficient, kind of clever. We don't have to go back to the drawing board and do a bunch of complicated proofs for the other 4 trig functions. Nope, we can actually just build their derivatives using the 2 rules we just figured out, plus some tools you probably already have in your calculus toolbox.
So, let's ask the question. How can we find the derivative of the tangent function, tan of x? How can we figure this out without doing a whole new proof? Well, the trick is to remember what tangent is really made of.
Right? It all comes down to that key identity. Tangent of x is just sine of x divided by cosine of x. As soon as you write it that way, the problem completely changes. It becomes something we absolutely know how to solve.
Because if tangent is a fraction, well, we can use the quotient rule. Remember that one? It's the rule that's designed for exactly this situation. Finding the derivative when you have one function divided by another. It's the perfect tool for the job.
Okay, let's just quickly walk through the steps. First, you set up the quotient rule with sine on top and cosine on the bottom. Then you plug in the derivatives we already know, cosine for sine and negative sine for cosine. When you clean up the numerator, you get cosine squared of x times sine squared of x. And what does that equal? That's right, it's our old friend, the Pythagorean identity, which just equals 1. So what we're left with is just 1 over cosine squared of x. And what's another name for that? It's secant squared of x. And there you have it. We just built a brand new derivative rule just by using the first 2. Pretty neat, right? No messy proofs required. Okay, let's get to the big picture now. We're looking for a pattern to make all this easy. Because when you see all 6 derivatives together, it can look, well, a little intimidating. But I promise there's a really simple trick to remembering them all. So here's the full table, all 6 of them. You've got sine, cosine, tangent, cosecant, secant, and cotangent. Now just ignore the letters for a second and only look at the minus signs. See them there? Do you notice anything about which functions have them?
Well, as this quote points out, there's a fantastic memory aid here. It says that the minus signs go with the cofunctions, cosine, cosecant, and cotangent. Those negative signs aren't just sprinkled in randomly. They follow a rule.
And here's the trick. Plain and simple. If the function starts with co, its derivative is negative. That's it. The derivative of cosine, negative. The derivative of cotangent, negative. The derivative of cosecant, you guessed it, negative. The other 3, sine, tangent, and secant, are all positive. Just remembering that one little rule basically cuts the amount you have to memorize in half.
So we've got the rules, we've got a trick to remember them, but what's the point? Why does any of this matter?
Let's look at a real-world application to see how these derivatives are actually used in motion.
Okay, think about a classic physics setup. You have an object attached to a spring, and you pull it down and let it go. It just bobs up and down, up and down. That's called simple harmonic motion. And that movement, it's a perfect wave. That means we can use a trig function to describe its exact position at any given moment.
So let's say the position of our object is described by the function 4 cosine of t. Well, if you want to know its velocity, how fast it's moving at any time, you just take the derivative. The derivative of 4 cosine t is negative 4 sine t. Easy. But what about its acceleration? You just take the derivative again. The derivative of velocity is acceleration, and that gives us negative 4 cosine t. See how each derivative reveals a new layer of information about how this thing is moving?
And that, right there, is really the key idea. The derivative is the language of change. It's how we connect position to velocity and velocity to acceleration. It lets us go from knowing where something is to knowing how fast it's going to knowing how its speed is changing. This isn't just for springs either. This is fundamental to pretty much all of physics, engineering, you name it.
So, to leave you with a final thought here, did you notice that cycle in the spring example? You start with cosine. The derivative is negative sine. The derivative of that is negative cosine. The derivative of that is sine. And one more derivative gets you right back to where you started, cosine. It's a perfect cycle of 4. And because it's a predictable cycle, we can figure out any derivative, not just the first or second. Which leads me to a little puzzle for you. What do you think the 27th derivative of cosine of x would be?